Hello and welcome. In this video, we're going to be talking about calculating atomic mass from isotopic composition. So let's go on and get into this. First thing that we have to do is talk about what an isotope is. So when we talk about an isotope, we're simply referring to atoms of the same element that differ in their number of neutrons. Remember, for an atom, you have protons and neutrons that are in that nucleus, and the electrons outside orbiting within an electron cloud. But it's those protons and neutrons that contribute to the mass of a particular element. Okay, so when we're looking at isotopes and the fact that they differ in their number of neutrons, because those neutrons are going to contribute to the mass of that atom of an element along with those protons, the mass of the atom of each type of isotope is going to be slightly different. And we don't record the individual masses of each isotope of an element on the periodic table. Instead, what we do is we report an average. Okay? And if we're going to report that average, then those differing masses of the isotopes must be taken into account when we calculate that average mass of an atom that ends up going on to a periodic table. Problem is, it's not just any type of regular average that we're going to be taking, where you just add up values and then divide by how many values you added. Instead, when we talk about the average atomic mass of an element, we're talking about a weighted average. This means that the more often an isotope occurs, the more it contributes to the overall mass of the atom as that mass appears on the periodic table. Therefore, the average mass is calculated based on the percent of each type of isotope as it occurs in nature. In other words, if we go out into nature and we get a sample of some type of element and we analyze it, we're going to find different percentages of each type of isotope of that particular element. And the higher the percentage of a particular isotope, the more its mass contributes to the overall average that ends up going on to the periodic table. So let's go on and take a look at some calculations. So in this particular example, we're looking at silicon. And we find in nature that there are three isotopes of silicon: silicon 28, silicon 29, and silicon 30, with percent abundances of 92.23, 4.68, and 3.09 respectively. And you'll notice that each one of these isotopes has their own unique atomic mass. But again, you're not going to find those three atomic masses on the periodic table. What you're going to have on the periodic table is the weighted average of these isotopes, again, based on their percent abundance. So here's how we can calculate this. There's actually two different schools of thought on this, but really and truly the math all comes out the same. But most textbooks, what they're going to want you to do is take these percentages, that 92.23, and they're going to want you to divide it by 100% and get a decimal of 0.9223, and then multiply that decimal percent by the atomic mass and get an answer. They would want you to do the same thing with the other two percentages as well. Okay. The other school of thought on this is, instead of dividing each percent by 100 and then doing the multiplying, getting your products, and then moving on from there, instead, go on and just multiply the percent as it's shown by that atomic mass, and then at the very end, you can divide your answer by 100, and it takes care of that percent. So the way I do it is I just leave it as the percents. So in this first case, I'm going to take 92.23, and I'm going to multiply it by this 27.97639. And the more decimal places you have in a measurement, remember, the more accurate that measurement is. And we're going to see how that affects things with another example in just a moment. So when I multiply, I get an answer of 2,580.312254. And that would be AMUs, atomic mass units. Now, other textbooks will tell you to go on and round to 2 decimal places for each one of these calculations, and that's perfectly fine. So we technically don't have to write that 2254 that's out there at the tail end. My next one, I'm going to take the 4.68%, and I'm going to multiply that by the 28.97649, and I'm going to find that that is 135.609, but rounded to 2 decimal places, that 9 is going to go on and round that 0 up to a 1. And then again, units of AMUs. Next thing that I'm going to do is take this 3.09, times it by the 29.97377, and get this answer as 92.618, etc. But round to 2 decimal places, it would be the 0.62, and then units of AMUs. Now that we have how much each isotope is going to contribute, we add those products together. So 2580.31, but I'm actually going to go back in my calculator, scroll up to the full unrounded value, just because that is more accurate. I'm going to do that for each one of my 3 answers, add them up, and I get 2,808.54 AMUs. And now I'm going to divide that by 100. And when I do that, that's just moving the decimal 2 places, and I get 28.085 AMUs. Again, you could round this to 2 decimal places and call it 28.09. Most periodic tables, though, record at least to 3 decimal places. And that's where this mass of silicon comes from on the periodic table. Again, it's a weighted average of these percent abundances for each one of silicon's isotopes. So let's take a look at the second one. This is rubidium. There's 2 isotopes for rubidium, rubidium-85 and rubidium-87. Their percent abundances of 72.15 and 27.85 respectively. And we can go through the math again. I'm going to show you a little bit of an easier method to do this instead of each thing into the calculator separately. You can set this up all as one type of an equation, where I do an open parentheses, 72.15, that's percent, times the 84.9118 AMUs, close the parentheses, plus open parentheses, 27.85% times 86.9092 AMUs, close the parentheses, and you can hit enter at that point and get an answer, and then you would take that answer and divide by 100. So that's what I'm going to do. Again, in the calculator, you would open parentheses, 72.15 times 84.9118, close parentheses, plus 27.85 times the 86.9092, close parentheses, go on and hit enter. I get 8,546.807, but I'm going to round that to 2 decimal places. That would be AMUs for the units, because eventually I'm going to divide by 100%, and that's where the units of percent end up canceling out. And when I divide that by 100, I get a final answer of 85.46. I wrote something wrong up here. Sorry. That is 8,546, not 44. I just read off my calculator wrong. My apologies on that. 6. And then again, AMUs. And just like before, this is where we get the mass that's on the periodic table, 85.468. So again, you notice, as I was mentioning before, the more accurate a measurement, the more accurate your final answer is going to be. And in most cases, they do round to 2 decimal places. But again, many periodic tables go to at least 3. So that is rubidium. So one more example, and this is bromine. If you'd like to pause the video and give this one a shot and then restart the video, see if you get the same thing that I come up with, please do so and be able to check your work. So if you pause the video, welcome back. I'm going to go on and work this problem. And I work it the same way as the previous one, but instead of rewriting everything out, because it's in this nice little table, I can set it up as such, but I'm still going to put it into my calculator as open parentheses 50.69 times 78.92, close parentheses, plus open parentheses 49.31 times 80.92, close parentheses, and hit enter. And when I do that, I get 7,990.62, making sure I read my calculator correctly this time. And then I'm going to divide that by 100. And when I do so, I'd get 79.906, with the 6 rounds that 0 up to a 1. And I get a final answer of 79.91 AMUs for bromine. And on the periodic table, notice 79.904. We lose some accuracy. The reason being, these two atomic masses are to 2 decimal places, whereas in our previous answers, we've had 4, 5, or more decimal places, making them more accurate measurements. And therefore, we get more accurate answers in the end. So those are 3 example problems that I'm hoping made sense to you. As always, if you have any questions, please feel free to leave me a comment or that question in the comment section. I'll be sure to answer as soon as I possibly can. Also, don't forget to subscribe to this channel so you don't miss out whenever I upload new content, more chemistry problems, procedures, things of that nature, just concepts. So if you're interested, please subscribe. Additionally, if you have any suggestions for a video, please let me know and I'll see what I can do about it. As always, thanks and take care.